In this video, I'm going to go through the process that you're going to need to go through to set your installation up to be able to do Monte Carlo simulation. So the first thing to do is to take a look at the current state of one of the model files, just to give you a sense for what we're going to be doing here and how this works. So we're going to cd into the Skywater /Skywater 130 PD or Skywater PDK. Let's see, it's under libraries, Sky 130 FD PR _Ngspice. And then we're going to go for latest and okay, so what we want to do is look under cells, and then this has all the devices like the NFETs and the PFETs. We've been using NFET 01v8, so let's go into that directory, cd NFET _01v8, and there's a lot of different files in here. The one that we're going to look at in particular is going to be Sky 130 FDPR NFET 01v8 TT PM3.spice. Okay, so let's less Sky 130 blah 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 TT PM3.spice. So you'll notice here there's this tantalizing block that is commented out, and these are mismatch parameters that are used by Cadence's simulator called Spectre to do Monte Carlo simulation, and this is not something that Ngspice knows how to deal with, and so they commented it out. And the way this works is that if you want to do a Monte Carlo simulation to simulate mismatch, what it will do is it will vary these parameters according to a pseudo-random Gaussian distribution with zero mean and a standard deviation, in this case of 1.0. By default, these parameters are defined to be 0. And if you come down here, the first place where, let's say this first parameter, Sky 130 blah 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 TOX E slope spectre is used is in this line down here, where it's basically multiplying. So this is a Gaussian random variable with a unit standard deviation and a zero mean. It's being offset by a value, and we have this this factor here, which kind of gives this Gaussian random variable or pseudo-random value sort of an appropriate scale. But then there's also this is the Pelgrim rule here, the mismatch rule, where there's some factor, some coefficient that's divided by the square root of the area of the device. Okay, so this is Pelgrim's mismatch rule. And the thing that we need to do in order to get this to work for Ngspice in a way that we can turn it on and off is to basically replace every occurrence of these mismatch parameters with a global parameter, which we're going to set to 0 if we don't want to simulate mismatch. We're going to set it to 1 if we do want to simulate mismatch, times Ngspice's built-in function for generating pseudo-random Gaussian random variables, and that's called a Gauss. And the three parameters are the mean value, the standard deviation that we want, and the sort of a parameter that lets us divide the standard deviation by something. I don't quite understand why the third parameter is. We're just going to make it 1. And so if this were just one file, we could do this with a global search and replace, and it would be good, but there's hundreds of files, and they're in subdirectories of subdirectories, and so the only way to do this is to write a script to kind of walk through the directory hierarchy and do this kind of global search and replace for us programmatically. And so that's what I've done. So I've got a Python script. You'll download it from the Canvas site. It's in my downloads folder. And what we're going to do is go over to my downloads folder, and take a look at it. So it's called process mismatch params.py. It basically just, so this is the name of the variable, the parameter that we're going to use to turn the Monte Carlo simulation on and off. It's going to be called MC_switch. And this basically just walks through the directory hierarchy underneath this cells directory and looks for files that end in .spice. Finds such a file, it basically opens that file up, creates a temporary output file, and then it starts marching through the file, looking for the mismatch block to basically build up the list of mismatch parameters it's going to try to do find and replace on. And then basically it looks for, once it gets past the mismatch block, it's basically looking for on every line an instance of one of the mismatch parameters that it found, and if it does, it basically does the replace, and it reports what it replaced. And then after the whole thing, if it's replaced something in that file, it basically backs up the original file with a .orig sort of suffix on the file name, and then it replaces the temporary file, the original file with a temporary file under the old file name. So that's how it works. We're going to now use it. There we go. So we're going to do this. It's going to be Skywater 1 PDK, libraries, Sky 130 FD, PR, and Ngspice, and then latest. And we want to copy that Python program in this directory. So the same directory that the cells subfolder is in. So we're going to do copy twiddle/downloads, process mismatch params to here. There it is. I'm going to run this with Python 3. And blam. There it goes. Okay. So if we go back to the cells directory under nfet 01v8, we can just look at we can see here that we have a bunch of new files that are here in white that are the modified files, and we have the .orig. And if we open up the one that we looked at before, we can see what it did. So if we less sky 130 blah 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 tt.pm3.spice, okay, we can see here that this occurrence of this what used to be sky fd pr1 nfet blah 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 toxe slope specter has been replaced with mc switch times a gauss 0 1.01. Okay, and it's done that a lot of times in a lot of different files. Okay, so that's all you need to do to process the model files. And then the other thing we need to do is we need to add the definition of that MC switch parameter to our code blocks that we incorporate to bring the models into our Xschem schematics. And unfortunately, because they're owned by root, the easiest way to do that is going to wind up being to use a text editor and edit the sim files directly. So we'll do that by going to cd, it lives in user, local, share, Xschem library, and then it's under the madvlsi directory. So there are all of our symbols in the madvlsi symbol set, and we're going to do sudo vim, and we're going to start with the FF models. And right here where it says value equals and then the dot option, wn flag equals 1, we're going to add a new line there, and we're going to say dot param mc_switch all uppercase equals 0.0. So by default, we're going to set this so that we're not doing mismatch simulation. Sudo vim fs models, and we do the same thing. Dot param mc switch equals 0.0. And now we'll do the SF models. Okay, so we're done with that. And now I just have a little test bench. I'm going to show you a simulation of some 4 transistor curves with and without the Monte Carlo simulation switch turned on and off. So this lives in download, documents, MC test. And so I've got 2, I've got the NMOS and I've got the PMOS version. So Xschem, we'll do the NMOS one. So there's my 4 NMOS transistors. This is the old TT block, so it doesn't have the MC switch in it. So we're going to delete that one and replace it with a new one from the library. And if I open this one up, you can see that there's the MC switch. Now it's set to 0. So if we do a simulation, it will be without mismatch. So netlist simulate. Now we're going to plot I of VI1, I of VI2, I of VI3, I of VI4, and we're going to do this with a Y log scale. And there are our transistor curves. You can see those look like a pretty typical NMOS transistor gate characteristic. The weak inversion regime here, strong inversion and moderate inversion, kind of in this regime here. And they're all on top of each other with no mismatch. So let's do this again. So we're going to just set the MC switch to 1.0 and save. Renetlist and then simulate. there are our 4 IV curves, but now they're not all on top of each other. So, and you'll notice here that in weak inversion, there's more mismatch than there is up in strong inversion. That's due to the fact that the mismatch in the threshold voltage becomes less and less significant the further and further above threshold you go. And that's really all I'm going to show you right now. I could do the same thing with the PMOS transistors, but it's basically the same thing. And so it's not super exciting. I do intend to do a follow-up to this video where I maybe show you how to do a batch of simulations where each one is kind of written out into its own output file using a control block to orchestrate the whole thing. So that'd be running, maybe it'll be like a CMOS inverter with looking at a voltage transfer characteristic with mismatch for some number of runs. So let's we'll do that in a different video that'll come out in the near future. That's it for now. Thanks for watching.